Okay. Do I need to respond to this, I guess?
No, I just sent you an invite, though, that should have gone to your email. Nope. Let me try it one more time. Oh, there you are, Doug James.
Found me?
I think this is you. Yes, this is you. Here we go. Go back to the plus page.
You mean the plus page that I closed?
Yeah.
That one?
Yeah.
I probably have it open down here. No, I don't. Okay.
All right. And I should get an invite here in just a second.
Will we ever get to tour the supercomputer?
Oh, absolutely.
Yes. Tomorrow morning session.
We're going to make you repair it.
All right.
We got this.
So we got to fix one
I'll
of
be
those
my
that
toolkit.
Absolutely.
you can,
I mean, we're going to practice.
Like, go find it.
Is that a TV or just
Now, if it matters
Do you have
again,
a problem with bugs in there?
oh yes. There is no serious computer program ever written.
Oh, I meant.
You meant creatures.
I meant like live bugs.
Yeah, but they're pretty tough live bugs because it's real cold. Yeah, these are
I sent him a link
butt
from the
chicken.
other page for my so can you click on it from there?
Let's see.
Share the event with them.
No.
No, that doesn't work.
Let me see here. Make sure you have all the plugins installed.
You won't.
Okay. Yeah, I do need to install the plugin. Might need you to type in your account. Maybe not.
Maybe not.
You have-
I'm crazy.
you have
I'm in
rights.
admin mode.
That's why I wouldn't get the invite, because I didn't have the plugin. There we go.
We'll give you the
web-based, huh?
link,
Yeah.
and then once you click on the link, it would bring you to the option to download the
Okay.
This was a terrible idea. Just saying. It was a bad idea. It was a bad call. Oh, man. Okay. This is how this is going. Oh, man.
Okay, looks like it's working.
It won't show the link.
Hmm. Sorry, Doug. No, it should be fine. I've gotten a lot of other people to just bring it right up.
So they do that. So even though it's like.
Oh, John's going to be using the Linux system.
Yeah, I talked to him about it already. How'd you get your inbox so empty?
It's a little crowded.
There's 3 emails in there.
Yeah. That's 3 more than I like to have.
Why is it not sending you the email?
You hit refresh, that might help.
Ah,
There we go.
there we go.
So you get him to join.
Yep, I got him to join. We're about to join the Hangout. Say I agree. Join. Now there's lots of me here. I'm over here. But then set it so that that's the video. And then we'll come over here and do a screen share. Full screen. Now, this is your presentation. And you look like you're good to go. Give me a holler if you have any problems. Should be all set.
Thank you, sir.
Yep.
Welcome back. I hope your heads aren't exploding yet. I would like to start with a computer. This is a PC. It may not look like a PC, but it's a PC. You can actually take this thing and hook a monitor to it, keyboard, mouse. In fact, we sometimes do. The only difference, or one of the differences, between this PC and the one that you might have at home is this has got a bit of an unconventional case. Now, this unconventional case is such that some people would call this a blade. A blade because you can take it and slide it into a case with other blades. And when you slide it into a case with other blades, and if you have enough cases, then you end up with a computer like Stampede. Stampede has 6,400 of these computers in it. If I told you that, I'd have to kill you. I don't know the answer. I mean, and it depends on how you measure the cost. Oodles and boodles.
You can pretty, in a broad sense, just say $30 million.
Yeah, it's about a $25 million computer. But it depends on what you count. It depends on whether you count the infrastructure, whether you count the cooling, the heating. But the computer itself is about a $25 million computer. There are about 6,400 of these. There's actually more, some of them with unconventional purposes. But the point is, there are about 6,400 of these blades. We call them nodes. And they work together in a way that puts the Stampede supercomputer at your disposal. The game is to figure out how to use all of these smaller computers working together in a way that allows you to get science done. Now, there's more. Each of these blades, each of these computers is no ordinary computer. This thing here is also a computer. At least they tell me it is. Those who know me around here know I've never turned mine on, so I can't be sure. But they tell me that this thing too is a computer. And it's actually a parallel computer. This particular phone happens to have 2 cores, 2 processors, 2 devices that are capable of executing instructions. And so this is a small parallel computer. This is a somewhat bigger parallel computer. This particular parallel computer has 77 cores in it. It has 16 on a main processor, I call them the 16 stallions, and 61 on the mini integrated, the mic coprocessor, I call those the 61 rabbits. So we have 16 stallions and 61 rabbits in each of these boxes. There are 6,400 of these boxes, and so behind you there is a supercomputer with 500,000 cores. The game is to figure out how to take advantage of that kind of processing power. And what I'd like to do is introduce you to this new world. We've spent a few days, and you've probably spent a few years learning a little bit about computing, learning a little bit about programming. Probably much of that time has been spent writing traditional programs. Now we're going to talk about writing parallel programs, how to use all of this processing power, these multiple cores, these multiple independent processors, in a way that allows them to help you do your science. Now, we're not going to turn you into parallel programmers in an afternoon. Just as Kent gave you a feel for what Fortran smells like, I'm going to give you a feel for what parallel programming smells like. My goal is to try to give you, to arm you with some of the big ideas, some of the big questions, some of the big terms, so that you can hold them up to the light and sort of use them as signposts over the next few weeks as you're becoming immersed in the details. You know, that maybe this will help you a little bit see the forest for the trees. The approach is this. I'm going to first spend some time talking about how the hardware, the nodes, the cores, the blades, affect the decisions we need to make and the work we need to do in our programming. And the first big idea is this. It doesn't happen for free. It doesn't happen magically. It doesn't just happen by taking this program you wrote for your PC, putting it on Stampede, pushing a button, and suddenly 500,000 cores are solving your... It doesn't work like that. We're also going to talk about the fact that parallelism is not a yes, no, on-off kind of thing. There are degrees of parallelism. There are types of parallelism. And we'll address that as well. I'm also going to spend a lot of time managing expectations. We have folks that show up on Stampede for the first day and say, okay, I want to see that program go 500,000 times faster than it did before. And no, it's not that easy. And finally, I'll talk about some of the other things that are important to keep in mind as someone new to this wonderful, wonderful world. I think we ought to begin with the literature. And I'd like to begin with my look at my discussion of maybe the most important, most interesting, most powerful book about parallel programming that I know of. It was written in 1876 by a guy named Mark Twain. And maybe you've heard of this book. It's called The Adventures of Tom Sawyer. It's, you know, you think it's a novel, but it's a book about parallel programming, because in this book, Tom Sawyer talks about persuading his friends to help him paint a fence. And the game here, then, is to understand that when you have more than one paintbrush, you can paint the fence faster. Or perhaps paint a bigger fence. The idea is we partition the problem into pieces, and we do those pieces simultaneously. And at the most basic level, that's what parallel programming amounts to. Partition your problem and work the pieces independently. In our case, paintbrushes correspond to the cores on Stampede. How can we break up our problem and assign pieces of it to individual cores? Now, one of the things about metaphors is they help make difficult ideas a little simpler. And if used right, they can give us insight into these difficult ideas. And so let me give you the first big idea that this metaphor suggests. If I can persuade 5 of my friends to help me with the fence so that there are 6 of us, we ought to be able to paint that fence faster. Maybe even 6 times faster. But probably not. Because the act of working together itself requires some coordination, some collaboration, some losses due to me getting in your way, us kind of working out who's going to do what to whom. You know, I reach into the bucket, and so you have to wait because you can't reach into the bucket to get your paint because I'm in your way. Those sorts of things. And so we would expect to do it faster, but maybe not 6 times faster. And that's an important idea. But there are other metaphors. Here's another metaphor. In fact, I'll give a prize to anybody who can name all the metaphors that I use in this talk because there are a bunch. This metaphor is...
Wait.
Yeah, there you go. Okay. This metaphor is parallel processing as mowing a lawn. Yes, sir.
So you were talking about how it's not going to like scale linearly because you add more cores. Is there some sort of function that models how parallel programming and multiplication of cores?
He said it's like not going to scale linearly. Let me translate that into English. What he says is that if we have 6 people working the problem, we should not expect to get 6 times as fast a result. And yes, in a few minutes I'll show you a more formal description for that. Okay? So, parallel programming is mowing the lawn. This particular lawn happens to be Augusta National near Atlanta, where they play the Masters golf tournament every year. And I'm here to tell you that's one heck of a lawn. And it's not a lawn that you could mow with a single lawnmower. The only way you're going to mow this lawn is by doing it in parallel, by bringing to bear multiple lawnmowers, in this case cores, to accomplish the task, partition the problem into multiple pieces, and apply pieces to each core. But there's a special lesson in this metaphor. This wouldn't work for me. I happen to have a lawn that is only slightly larger than a typical postage stamp. And I'm here to tell you that this approach is not going to work. You couldn't get 2 hand mowers on my lawn. And if you did, they would get in each other's way in such a way that the problem just is not big enough to exploit the power of parallelism. The metaphor here that I'd like to offer is that for a given problem, there's a sweet spot. There's a natural level of parallelism associated with your scientific problem. It may be that until you reach that level, you can't solve your problem. But if you go beyond that level, you're going to be frustrated. And part of the game is to understand the sweet spot. Let me put it another way. If your goal is to add 10 numbers, then I'm here to tell you, you don't want 11 processors. I'm guessing you could see that. But you know what? If your goal is to add 10 numbers, no. If your goal is to add 10 billion numbers, you still don't want 11 processors. You know why? Because these dagnab things are so fast that depending upon whether you're talking about mud cores or the normal, regular, run-of-the-mill stallions, each of these cores, working alone at full tilt, can do on the order of 20 billion calculations a second. And so they're pretty dagnab fast. Your problem's got to be pretty big before it's worth the trouble to do the coordination necessary to partition your problem and do it in parallel. Now, a third metaphor. Oh, I can't count them for you, can I? That's no fun.
Wait a second.
Okay, now, have you already lost count? Try to keep up, will you? Okay. Okay, he's no longer in the run. Okay. Third metaphor. Solving a jigsaw puzzle. Now, what I'd like you to do is imagine that you've gotten your friends or your family together and you're going to work together to solve a jigsaw puzzle. Now, an eminently reasonable way to solve that jigsaw puzzle would be to sit at a kitchen table, put the pieces in a bowl, and each of us sit around the table and we reach in and get the pieces we want and we work the puzzle. And, you know, maybe we coordinate, maybe we talk, maybe we look for corner pieces. You know, we kind of strategize. But the point is, there's a bowl of shared puzzle pieces that we all have access to. This, too, is a wonderful metaphor for something that begins to resemble a no-kidding, serious programming model. Because this blade right here, actually half of this blade, is a computer that consists of cores that all have access to the same bowl of puzzle pieces, the same RAM, the same shared memory. This is a shared memory computer. Now, I'm actually lying. I'm going to explain how I'm lying in a minute. But for now, let's pretend this is a lie, but it's a useful lie. This is a shared memory computer. It happens to have 16 people around the table, 16 cores, all having access to the same bowl of puzzle pieces that we call RAM, memory. They share the memory. And just as the people building the puzzle have as their great challenge trying not to get in each other's way, you know, I reach for puzzle pieces and you can't get to them, or I have the piece that you need, or I'm working in a corner and I prevent you from being able to work there or see there. Just as the game is a game about coordination and making sure the shared resources are shared in a coherent way, in the same way, if I have a shared memory computer, the programming challenge is one of coordination, making sure that your access to memory does not interfere with mine. Now let's make this more concrete. If you've ever collaborated on a paper or a spreadsheet, then you know what I'm talking about. You know what a pain in the you-know-what it can be if somebody's modifying something and somebody else is modifying at the same time. You know what it's like if 3 people are modifying a spreadsheet, the last person in wins, and there's no telling what is in that formula anymore. This is the challenge when programming a shared memory computer. The principal programming model, the primary way that we do this is with a programming model that's called OpenMP. MP happens to stand for multiprocessing, but the point is, OpenMP is a mechanism for basically sharing work across cores that all have access to the same shared memory. An OpenMP program is a program that is a single binary, a single executable, that knows how to divvy work to the cores and basically assign them independent tasks. Now, I've been looking for the right metaphor to explain how this is done. It's done with something called threads. Some people call them lightweight processes, but that's just a word. The best metaphor I can come up with, and I don't like it yet, is a really, really smart octopus. Imagine an octopus whose, will you forgive me for not saying tentacles, whose arms, okay, are all doing something different at the same time. They're sorting marbles or they're working on puzzle, and so the octopus is basically partitioning the problem in ways where each of the arms is separately, independently executing on behalf of the single program that is the octopus. Each of those arms is a thread, each of those arms is a core, and each of those arms has access to the same bowl of puzzle pieces that is the shared memory computer. The key idea here is one executable. One executable, but independent threads of execution within that executable. And all of those independent threads have access, in theory, to the same hunk of memory. And it's the programmer's job to not only divvy out the tasks, but to manage the memory so that the tasks have access to the memory they need, but they're protected from each other so they don't step on each other in ways that create unpredictable, incorrect, or incoherent results. OpenMP. But that's not the only way to play the game. Let's go back to the puzzle pieces, but this time we're no longer solving some 500-piece jigsaw puzzle. We're solving a jigsaw puzzle that's the size of your average football field. I'm guessing that you'll agree that we're not going to sit around the table and do this with the bowl of pieces in the center. That's just not a workable model. In fact, to use an overused phrase in the supercomputing business, that's just not a scalable approach. We're going to have to come up with another approach. And the approach that you might come up with, if you thought about it a while, is to come up with a whole bunch of teams of people. You know, maybe 50 teams, each of which has their own bowl of pieces and their own table, and they're going to sit at their own tables and they're going to work a piece of the problem. Maybe, if you're lucky, the bowls all have pieces associated with the piece that they're working on. Maybe not. But one way or the other, we now have a new programming challenge. In fact, we have a new architecture. Because all of a sudden, the people that are building the puzzle no longer all have access to the same shared puzzle pieces. You've got your own, and I've got mine, and you've got yours, and we can't get to each other's shared puzzle pieces. We don't have shared puzzle pieces anymore. We got a new problem. And you know what? It's a problem familiar in a supercomputing world. Because there are computers out there that have many cores, but each core has its own RAM. And you might say, why would we do that? Well, it's just too expensive to build a computer with a whole bunch of cores and huge amounts of RAM. So we have RAM. We have nodes out there back in Stampede that have a terabyte of RAM. 32 cores and a terabyte of RAM. But it's really complicated and really expensive to do much more, to do much better than that. And so we need another approach. And the other approach is each core has its own RAM. Each puzzle solver has his or her own puzzle pieces. And I think you'll agree that we now have a new programming challenge. Now we have a programming challenge that is one of communication. There's no longer a danger of me getting in your way because I got my own pieces. But now the danger is maybe I need the pieces you have, maybe you need the pieces I have, and we need to communicate in ways where I become aware of your needs, you become aware of my needs, and I supply you the pieces you need, and you supply the pieces I need. And I'll bet, if you thought about it a while, you could come up with a workable solution to how you might build a football field-sized jigsaw puzzle with 50 or 100 people. You know, come up with communications mechanisms that would allow you to do that. And I'm betting that if you did it once, you might muddle through, and then you'd improve the process, and you'd tune, and you'd optimize, and you'd improve, and 3 months from now, you'd have the world's fastest football field-size puzzle-solving team because you had optimized your process. Well, this too is something we do all the time, but we have a different programming model. The programming model is no longer one of avoiding stepping on each other. It's no longer one of managing shared memory. It's now about communication. And the programming model that we use, there are many, but the most common, most important one is called MPI. It stands for Message Passing Interface. And the very name suggests its main purpose. It's about communication. But an MPI application works differently than an OpenMP one does. In an MPI application, there are many, many, many programs, binaries, all identical. And what the MPI infrastructure does is it launches a copy of your program on every single core. And then you write the program so that the individual copies know how to talk to each other. And the MPI infrastructure provides essentially communications mechanisms and startup mechanisms that allow all these programs to work together. Now, you might say, what good is a program where every single program does the same thing? The answer is they do the same thing, but they are allowed to be aware of their serial number, their rank. When they wake up, they say, which number am I? Oh, I'm number 17? Oh, I'm supposed to process the 17th piece of data. And I'm supposed to pass information to number 18 and 16. And you write the program in what is called a rank-aware way. So every program does the same thing. They're all waking up. You know, you wake up and say, oh, I'm number 13. I have to pass information to 12 and 14. And you wake up and you say, I'm number 6, and I have to pass information to number 5 and number 8. You know, those are number 5 and number 7, those sorts of things. Many copies of the same program, all running in what is called a rank-aware way. Now notice what we've done. 2 computer architectures, 2 programming models, and they're very, very different. And neither one of them is the one we use on Stampede. Because Stampede is neither a shared memory machine nor a distributed memory machine. It is both. This is a node. It is a shared memory computer. There are, on a typical one, there are 16 cores, each with access to a shared pool of 32 gigs of memory. There are actually 2 chips with 8 cores, but more or less it's 16 cores with access to 32 gigs of memory. But there are 6,400 of these hooked up in a distributed way. So the cores on each node can see the same RAM, but they can't see the RAM on the other nodes. And so this is a computer that's sort of a hybrid. It's sort of a mixture of distributed and shared memory. Each node is a multi-core shared memory computer. It runs its own operating system. And then they're connected high-speed network in a way that make them act like a distributed computer. Well, how do you program this? Well, there are a lot of ways you could do it. One way you could do it is to just pretend that it's a distributed memory computer and completely forget that some nodes can share memory with other nodes. So you could write a pure MPI program and just know that as long as you're communicating, who cares if it wasn't necessary? That's actually a pretty good model, and it's a common model. In fact, the MPI libraries usually are smart enough to know if he asks if he's number 16 and he's communicating with number 15 and we're in the same node, the MPI libraries are usually smart enough to know whether he and I share memory, and they do the communications. You know, they kind of take advantage of the architecture in the hood, but I can program in pure MPI. Another approach I could take is a hybrid model. It's not for beginners, but it's a hybrid model where I use MPI to communicate between nodes, and I use OpenMP to work on node. That's a pretty good model. It requires a bit of sophistication, but it's a pretty good model. I could write a pure OpenMP code, but when you do that, you need to remember that OpenMP means shared memory, and you are confined to a single node. You can't write an OpenMP program that can take advantage of all of Stampede. It doesn't work. OpenMP is like the octopus. All the arms have to have access to the same memory. Now, we could do any of these things. Yes, sir?
So, like, if you have, like, if you label this 1, 2, 3, and 4, and let's say, like, number 3 has some trouble doing his job, he has to return his job to 2 and 4, but because he doesn't share his memory, can they, like, help him somehow?
Well, the question is, suppose number 3 is sick. Suppose there's a fault on number 3. There's, you know, some hardware problem. You know, can the program sort of adapt to tolerate? Is that a fair assessment?
More so like, let's say that number 3's job is just harder, so it takes him more time.
The question might be about faults. It might be about load balancing. It might be whether I have more work to do than you. The answer is, it depends on how well the program's written. You know, I can write the program under the assumption that all the pieces require equal amount of work. I can write the program under the assumption that if I finish my job, I can go to a queue, a line, and pick up the next piece of work. It's the capability to write a flexible program is certainly within the functionality that these programming models provide. But as you can see, the devil's in the details, and it has to do with the amount of time, the skill, the flexibility you build into the program. Okay? Now, we could employ any of these models, but you know what? We don't use any of them because none of them apply, because this isn't the way Stampede works. There's another level of complexity. You see, here's the node, but on essentially every one of these nodes, we hook a mic coprocessor, a Xeon Phi mic coprocessor, many integrated core. This is the 61 rabbits I talked about. We hook that to the node. And so this is a shared memory computer. This is a shared memory computer, but it's a shared memory computer that more or less can only talk to this shared memory computer. This one has 61 cores and 8 gigabytes of memory. A little slower, a little less capable, because it's low power. But we need programming models that, if you will, honor this. And this is no small matter. On Stampede, if you just looked at the main processors, the traditional main processors, you've got about 2.2 petaflops of computing power. When you add the mics, you're up to 9.6 petaflops. It would not be a good thing for you to leave either one on the table. And so we'd like some models that exploit this. Now, that's not for beginners. But one way to do this, one way to use the mics, is to recognize that they are computers all by themselves. This is, I apologize, it's difficult. This is a blade. This is a blade split in its 2 parts. The main processor with its 16 stallions is here. This is the mic coprocessor. It's got 61 lightweight cores on it. Each share the 8 gigabyte. They share the 8 gigabytes of RAM, and you can program the mic as a standalone computer because it is. You could also program the main processors, the main computers in the nodes, which we call hosts. You can program the hosts and the mics so that they each run MPI tasks. So, you know, you could put 2 MPI tasks on each mic and, 4 on each host and do that across 1,000 nodes. You know, you could do that. That's sometimes called symmetric operation. You can also use the mics as assistant processors, sort of pocket calculators for the main host. So the hosts have a job to do. Maybe 1,000 hosts have work to do, and the hosts just sort of, assign pieces of their work to the mic in what's called offload mode. Now, do you have the idea there's more here to learn than we can teach you in an hour? Absolutely. But you can see that there's a world of opportunity here, and that this is worth pursuing. Well, let's talk about it a little bit. I said that parallelism wasn't a yes or no kind of thing, and I'm guessing you're starting to believe that. So let's talk about levels of parallelism. And I'd like to begin with what I consider to be the simplest possible example of partitioning a problem and doing it in parallel, what you might call the needle in a haystack problem. Now, if you think this is a silly problem, I'm here to tell you there are a lot of important scientific problems that amount to finding a needle in a haystack or many needles in the haystack. Let's think of some, shall we? I'm a humanities scholar studying Homer, and I want to understand how many times a certain adverb occurs in close proximity to a certain verb. Do you agree that I could assign chapter 1 to one core and chapter 2 to another and chapter 3 to another without any difficulty whatsoever? You know, I could partition the problem in ways that allow me to do that. Perhaps I am a computational biologist and I am trying to do some, I've got a piece of a gene, I'm trying to find a match, right? When I find a match, I'm done. Or maybe I'm trying to find a protein binding site and I want to, check 5 or 6 or 1,000 or 1,000,000 orientations of one molecule against another. Can you see that essentially I'm searching through a lot of possibilities until I find them or assess them or count them? I could be a climatologist or studying maybe evolutionary ecology, and I want to understand the way insect populations, I'm amused she was asking about bugs and stampedes and she meant insects, okay? I want to see how the insect populations respond to these dozens and dozens of climate conditions, winds, temperature, humidity, and I want to try them all. In a sense, this amounts to exploring needles in haystacks. So this is real science. So one approach to parallelism is what you might call thinking top-down, thinking coarse-grained, and partitioning the work into essentially independent tasks. Chapters in a book, a collection of orientations for the binding site, chopping up the gene into pieces. And this is an eminently reasonable approach to parallelism. So essentially what you would do is you would have cores or nodes, each of them assigned to tasks that generally amount to breaking up the data and doing the same job on the data. So a single program operating on multiple data sets might look like this. My application is running on many processors, and it's checking, wind conditions 0, 1, 2, and 3. Or piece of the gene 0, 1, 2, or 3. Or chapter in Homer. I don't think Homer has chapter 0, but you get the idea. Okay? And this is an eminently reasonable approach. It's a common approach. It's an important approach. It's the most basic approach. And what it says is the same computer program is running on different data. The logic within the program may differ based on what data you have. That's okay. And the game becomes how much communication, coordination, and synchronization you have to do. For example, if the game is literally to find the one binding site, then when I find it, I send out a message that says, okay, everybody stop. If, however, the game is to assess, the communications might amount to, okay, what'd you find? Let's compare it to what I found and let's see who wins. If the game is to collect, we have to all finish. If I finish early, I might say, anybody got something I can help you with? Or I might shut down. In the simplest case, we have what some people call massive parallelism. Some people call embarrassingly parallel because there's not much complexity to the program. It's becoming more and more common to remove embarrassing and say pleasantly or some other, euphemism. But the point is, it's a problem where there's little to no coordination required. High degree of independence. Chapter 2 really is independent from Chapter 1. And this is important science. this kind of science, another important example, well, one of the important examples is parameter sweeps. You know, you need to test the response of your system to a lot of different possibilities. If you're doing this on Stampede, you should know that we have tools that make this easy. We have tools that allow you to bundle dozens or hundreds of, you know, examples of running your program against different data sets. You know, these kind of problems typically are, you know, you don't really have a parallel program. You just have 10,000 of them. And if you have 10,000 really simple parallel programs, we got a tool that amounts to a box where you can pour them all in and launch one job and run them. Okay? And I recommend that you become aware of that because it's kind of nice. But life isn't always that simple. And sometimes we have problems that are not particularly embarrassing with parallel. In a typical example, we might take a seismic region and chop it up into parts, or we might take a galaxy or a part of the galaxy and chop it into parts, or we might take an airplane flying through an air mass and chop the air mass into parts. And what we might do is try to approximate the differential equations, describe the phenomenology, and when we do that, what we end up with is matrix equations with millions and billions of unknowns. And it seems like the partitioning is easy, but the complexity comes in where the regions touch each other, and the problems associated with them are very, very complex, especially when the domains are irregular. And this process is called domain composition. It's extremely important, but the challenge is in what are sometimes called the halo, transition, or boundary regions. It's where the domains touch each other, in the communications associated with those, and based on the question we just asked in the load balancing. You know, if you are modeling the universe, and we have people that model the universe, or you're modeling seismic activity under California or Japan or some part of the Pacific Rim, and something interesting starts to happen, the computational complexity in the interesting region might be higher than it is in the uninteresting region. If the galaxies are starting to collide in your model, there may be more computations to be done, and I might not be able to figure out what those computations are until they happen, and so I may end up with 400,000 cores of Stampede sitting around hands folded waiting for 100,000 to finish the hard stuff. And so there's a lot of work to be done here. Now, that's top-level parallelism, chopping the problem into big tasks and partitioning the tasks. There's another kind of parallelism at the exact opposite end of the scale. Now, my wife is a farmer's daughter. If you know anything about farming, you know what that machine is called. It's called a combine. And you know, the farmers drive that combine during harvest time. And it's called a combine because it just... I bow before you. I have always wanted to drive a combine, but my in-laws don't trust me to drive the combine.
Oh, it's automatic. Pretty much. Going the direction.
I'm going to tell them you said that. Would you? No, that's pretty cool. Yeah, but you know, combine is called a combine because it combines a bunch of tasks. Pretty cool, huh? But one of the things I want you to notice about this combine, and even my wife, who claims to know everything there is about farming, admits she doesn't know if this is a corn or a wheat combine. But I think you don't have to be a farmer to see what this thing's doing. What's that? When you drive this thing, or when she drives this thing's doing more than one row at a time. You get parallelism for free. You don't have to partition nothing. You drive down the row, and that one farmer gets 10 rows at once. A very fine-grained, to get it grained, calculation. Okay? One core, one farmer, one combine, multiple calculations. And you know what? It happens on supercomputers too. Now, here's a typical loop. For I equals 0 to a gazillion, you know, add these two arrays and produce a third array, you know. So A2 plus B2 is C2. A3 plus B3 is C3. And you can see that there's a gazillion calculations to be done. You can see that they could be done independently. You can see that this is the same whether you're in C or Fortran. But here's the really cool thing. On a modern supercomputer, each core is like one of those combines with the forks, and it can do more than one of these things at the same time. In fact, on the host here, you can do 4 numbers and 4 numbers and add them together. In fact, you can add them together and multiply by a third set of 4 numbers each clock cycle. And in fact, on a mic, you can do 8 at a time, and these are double precision numbers, and you can do product and addition to produce a result, 8 double precision calculations like this, a total of 16 double precision calculations every single clock cycle. More or less for free, as long as you're talking tight inner loops that are doing simple things over and over and over again. But if you are a computational mathematician, and I heard some of you are, you know that this calculation is a pretty important calculation that shows up a lot in matrix work, and much of what we do is matrix work. So this kind of calculation is pretty important, and it's called vectorization. So we've already seen 2 kinds of parallelism, sort of task-based high-level parallelism, and low-level, sort of fine-grained vectorization. One is about partitioning the problem. The other is about tight inner loops with simple calculations. I should, before I mention the third type, I should mention that one thing that's cool about vectorization is, in the best of worlds, the compiler will do it for you. You basically just hand it your code, it can see that inner loop and say, you know what, I can do this. Okay? The game becomes not doing anything to get in the way of the compiler, like putting print statements in the middle of your loop, or making your loop too complex, or making it hard for the compiler to figure out where the data is going to be at need. You know? The problem is that these things are so dag-nab fast that feeding it enough data can be hard. And the problem sometimes is how many loads it takes to get into the vector register, making sure the data's, you know, kind of aligned and just sort of, you know, it takes some work. But the thing that's cool about this is it can be done more or less automatically. There's a third kind of parallelism. And I actually pulled this from a real-world fluids algorithm that consists of steps. And it's not important whether you know what these steps mean. You know, they sound hard, right? Compute the gradients, you know, we solve for the momentum, and then we compute the fluxes, and then we solve for the, you know, the doobie-dabbity, you know, it's got steps. And you know, whatever your discipline is, you got steps, right? And one of the things that you might do is ask yourself whether one of those steps is something that can be parallelized. So, for example, there's a step in this algorithm, there really is, it's not important which step, that consists of, for each cell, for each piece of your domain, find the critical points of that cell. Doesn't that sound like something you could parallelize? Doesn't it sound like something that you could say, you know, dear 16 cores, would you guys each work together, each of you take a cell, and when you're done with your cell, go on to the next cell? Doesn't that sound like a step we could parallelize? Doesn't it sound like something we could do where we just basically say to OpenMP, dear OpenMP, spread this loop across the threads. And you know what? It's that easy. In many cases, with one line, you can put on top of that, dear OpenMP, thread this for me, will you? Now, I'm holding back a little bit, but it really can be that easy. And you know what's really cool about this? Is this can be a really good way for some research group that has never ever done parallel programming to sort of take the first step and move into this incremental. You know, instead of rethinking the entire program, which could be, you know, thousands and tens of thousands of hours of work, is to look at your program and look for opportunities to parallelize this loop, especially if you look at your program and saying, you know what, of these 5 steps, boy, it's the fluxes that are killing us. The fluxes are 2 days worth of work and everything else is 5 minutes. Wouldn't it be cool if we could parallelize the fluxes? You know, I don't give a flip about the rest. Let's focus on the fluxes, and when we're done with the fluxes, we'll look at something else. That's a common approach, and it's a good approach. Now, when you really, really dig in, you employ this at multiple levels. And there's no one way to do this. But a typical approach might look like this. A typical approach might put together MPI and OpenMP and vectorization in the following way. You split up the domain. You know, the north of the United States and the south of the United States and the west of the United States and the east of the United States are each going to be assigned to a node. And they're going to communicate by MPI. And then on each of those nodes, we've got compute critical point kind of work to do that will thread. We'll use threaded parallelism to complete the work. And within each thread, there's gazillions and gazillions of calculations to be done where we bring out the combine and let those tight inner loops get vectorized. Now, that ain't for beginners. And it's not without its decisions to be made. Like, if you try to thread something that is better done with vectorization, you might not get as good a performance as you anticipated. But it's pretty cool when you think about the possibilities. In fact, it's pretty cool for another reason. Yes, ma'am? Did you just moan and groan about linear algebra kernels? Do you know that my specialty is linear algebra kernels? I am personally offended by what you just did. You know, I used to like you because you drove a combine, but I don't like you anymore. No, the good news is this. The good news is this, that, you know, there are a lot of people out there that have spent tens of thousands of years of labor writing parallel libraries that do a lot of the things that are really, really important in this business. And one of the things that's really, really important in this business is matrix calculations. There's an awful lot of science that amounts to starting with partial differential equations and, you know, partitioning or discretizing to form what amount to huge linear systems, matrix equations. And there's a lot of folks that have written matrix solvers, linear algebra kernels, and I have to tell you, they're pretty dagnam good. And unless your needs are very specialized, or unless your goal is to research the very nature of these kernels, it's going to be hard for you to beat them. You'd be crazy to do something other than call these libraries. And I'm particularly big on MKL, the Intel Math Kernel Library, because they're built by Intel, and they support the mic, and they support the mic in very sophisticated ways. You can get some parallelism, you can get some mic capability for free by just calling MKL and let MKL handle the details for you. So, you know, don't write your own matrix solvers, you know, unless your goal is to study matrix solvers. What is the what? There is, and if I liked you, I'd tell you what it is. No, it's a library for solving systems of equations, matrix problems.
Yeah, is this like a program or it's just like a library?
A library is a set of pre-compiled subroutines that your program can call. You know, it's like when you fire up Microsoft Word and you do spell checking, Spell checking is done by a library that's making something available to my
Yeah, I was wondering which program or where can I use the MKL? Like, is it in C?
Okay. MKL, you can call it from C or Fortran. But if you have an R program or a MATLAB program or a Python NumPy and R and MATLAB are calling MKL under the hood, or can be made to call MKL under the hood. And so you can get a lot of parallelism for free, including mic-based parallelism, if you understand how to exploit the fact that MKL knows how to do this. And we teach classes on that for the people we like. And you know, so I'm pretty big on MKL. Thank you for being a good sport and let me have some fun with that. Now, that's the good news. Let's talk about the bad news, okay? Because a lot of times people get all pumped up about this, and then we gotta, you know, get them to breathe in to a paper bag and kind of bring them back to earth, because we have to manage expectations a little bit. And I think it's important to manage expectations. I said, and I meant it, that if you get 5 friends to help you paint a fence, you are probably not going to be able to paint the fence 6 times as fast. That's a fact. And what I want to do, based on your question, I want to quantify this a little bit and make this notion a little bit more precise. Now, don't panic about the equations. They're not that hard. What I'd like to tell you is that when I tell you that 6 people working together might be able to paint a fence 6 times as fast, or might not be able to paint a fence 6 times as fast, I have just used the most natural notion in the world of speed up, which is the time it takes to do the job by yourself compared to the time it takes working together. If working by myself takes 6 hours and working together takes 1 hour, I got a speed up of 6. Agreed? And that would be perfect. It rarely is perfect. And there's a graph of number of processors, number of cores, number of paintbrushes versus the speed up. If it were perfect, it would climb in a straight line that had a slope of 1. It rarely is perfect. And it's rarely perfect for a lot of reasons. I call it the cost of coordination. Okay? There's bumping into each other and planning to be done. It's rarely perfect, but that's what speed up is. Sometimes we measure it in terms of efficiency. You know, did we get 100% perfect efficiency? Well, what would that mean? It would be comparing the speed up to the number of paintbrushes or people involved. You know, if you take speed up of 6 and divide it by 6 cores or 6 paintbrushes, wow, that's 100%. That's pretty good. So another way to measure this is efficiency. Speed up divided by number of processors. And, you know, it's not rocket science. I do think that it's probable that if you're seeing these for the first time, it may be hard to keep it in your head all, you know, for the rest of the talk. But these are very simple notions, very simple metrics. They're the metrics that you would come up with if you were trying to quantify this. And what I want to do is use these metrics to understand, the nature of computation. The first thing I will tell you is you should expect to lag behind perfection, and in fact you should expect a sweet spot beyond which throwing more people at the job makes it worse. It's the old, you know, if the lawn's too small, don't bring too many lawnmowers. If you have a fence that's the size of this screen, you probably don't want 30 painters. And if you're adding 10 numbers, you dagnab well don't want 11 processors. There's a lot of reasons for that, but I want to talk about one that you wouldn't think of, and it may be the most important. Let's talk about baking a cake. Okay? Let's assume that it takes you 2 hours to prepare the cake for baking, and another half hour to bake the cake. So it takes me 2.5 hours from the time I start until the time I finish. But I'm going to get some help. And so what I'm going to do is I'm going to bring in a friend who is so good that we work perfectly together. No wasted time, no overhead. Man, we can read each other's minds. We never get in each other's ways. We work well together. And so I'm here to tell you that we can now take that 2-hour prep time and cut it down to 60 minutes. And then it takes 30 minutes to bake. And so 2 people working together, no losses, perfect communication, can bake that cake in 90 minutes. What if we have even more cooks? Well, let's go ahead and graph. Let's graph various things: the time, the speed up, and the efficiency. So we've already done it for 1 cook and 2 cooks. Let's now do it for 3, for 4, for 5, for 19, for 20 cooks. And again, let's assume, and it's completely unrealistic, but let's assume that those cooks are perfect at coordinating, no losses, they read each other's minds, perfect efficiency. So for example, by the time we're down to 20 cooks, or up to 20 cooks, man, it's only taken us 6 minutes to prepare that cake. But you notice something? It still takes 30 minutes to bake it. No matter how many cooks I have, if I could do the prep time infinitely fast, how long would the job take? 30 minutes. I can never do better than 30 minutes. Why? Because there's an inherently serial part of the calculation. There's a part that cannot be partitioned. There's a part that has to be done all by itself. 3 women cannot have a baby in 3 months.
Wow.
Now, that's an important idea, because in every one of your problems, scientific or real world, there is a portion of the labor that can be done in parallel and a portion that cannot. And you know what? The part that cannot be done in parallel, by its very nature, is the part that is sort of the long pole in the tent, that's restricting, that's sort of the boundary, the wall that determines your performance. Now, if I were teaching a formal class in parallel computing, we would have as an exercise deriving the limits that this particular phenomenon gives us, and it's called Amdahl's law, and it's a fancy little formula that you can use to impress your friends. But you know what it says? It really says that your speed up will never be better than what you can achieve with perfection on the parallel section. And in fact, that will never be as fast as what you could achieve if you were infinitely fast on the parallel section. And you know what that means? That means if you're baking a cake and 1/5 of the time required is serial, then your speed up can never be more than 5. The reciprocal of your serial fraction is the bound, the theoretical bound that you can never beat. And you know what? You're probably not even going to achieve that. That's perfection. That's inherent in your problem. It's the nature of the work that you're doing. Now, some people argue that this is an unrealistic and unimportant law because they say that's not the way it happens. They say, you know what? Okay, your serial fraction is a severe constraint. You know, you reach a point where there's diminishing returns, where adding processors doesn't really help. Agreed. They agree with all this, but they say that's not really the way it happens in the real world. The way it happens in the real world is, if you add processors, you solve bigger problems. You don't try to solve the same problem with more processors. You try to solve bigger problems with bigger processors. And you know what? There's a law for that too. And it's a little bit more complicated, and it's also a good homework exercise, but it basically says that if you're willing to define speed up in a way that honors the growth in your problem size, then you can get incremental benefits from adding processors. But you're still restricted in an important way by the serial fraction in your code. And so part of the game is to understand that, because you can never overcome that. Other issues. One of the things that I try to teach middle schoolers when I talk about computer programming is I try to help them understand that computers do exactly what you tell them to do. Now, if I were being a negative, if I were a nattering nabob of negativism, I would say that God, I just lost it. Whatever. Computers do exactly what computers can't read your mind. They don't do what you meant to say. That's what I was trying to say. Computers do not do what you meant to say. In fact, you probably wouldn't want them to do that. Have you ever gotten, the computer doing your text complete and you get annoyed because it's guessing wrong? Computers don't do what you meant to say, and your program will happily execute your incorrect code. We know that, right? Anybody that's ever been near a computer knows that. But what I'm telling you is that this is aggravated when you're working in parallel. It's aggravated in ways that you have only begun to imagine. And one of the reasons it's aggravated is the phenomenon that we talked about, that working on a spreadsheet together, where last one in affects the results, where it works fine on one core, but it doesn't work fine on 50. Or it works fine on 1 and it works fine on 2, and it doesn't start to do funny things until 100. And so one of the things that's hard about parallel programming is to understand and manage and study and predict and analyze the ways in which the parts of your program interact that you hadn't anticipated. And I'd like to illustrate with some examples. And these are cooked up examples, I admit it, but I hope they are helpful to you. I've thought of some simpler ones, and I might actually replace these one day. But here's the first example. You're adding 2 arrays to produce a third array. So you've got a long list of numbers. Let's say 1,000 numbers. You've got 1,000 numbers in array B, 1,000 numbers in array C, and you're adding them together to produce 1,000 numbers in array A. So the 12th component of B plus the 12th component of C equals the 12th component of A. I think you'll agree that the operations, if you're doing 1,000 of these, are independent. That I can split these up across cores. And that's true. This is an independent and safe loop in the sense that I can parallelize it. I can do this any way I want. I can vectorize it. I can assign it to threads. If it's big enough, I can give MPI tasks pieces of this loop. This is safe. The operations are independent. But if you look at this one, I hope you'll agree that this one's not safe. I hope you'll agree that order matters here. In this case, what we're doing is the 100th value is the sum of its neighbors, this one and this one. Well, can you see that if the value here depends on this one plus this one, that I'll get a different answer if I update this one first than if I update this one first. That if I do this from k equals 2 to 999 in order, I would get one answer. But if I did it from 999 to 2, I'd get a different answer. And if you're not convinced of that, try it. And boy, if I assigned it to threads and I didn't know what order those threads were being executed, Lord only knows and Lord's not telling. So this is unsafe. Order matters. I cannot parallelize this loop as written. Here's an even trickier one. I taught high school programming. In high school, the game was, what if I have 2 things in my hand and I want to switch them? Well, what I have to do is I need a temporary location first to set one down. That's the way you switch things, right? And if I did that, thank you, sir. If I did that on a computer, if I have, you know, two values that I want to switch, I need a temporary storage location. If I wanted to do that 1 billion times, this is how I do it. Is that safe to do in parallel? Depends. It depends on whether the temporary location is shared or not. I mean, what would happen if I was trying to switch these, and I set this down, and these two guys were trying to switch things, and they picked this one up? I mean, we could end up, who knows what we could end up with, right? I mean, this is potentially unsafe, and it depends on how we manage the storage. You know, we could prevent the problem by sort of locking the storage. You know, say, you can't do this going done. And that's actually quite common. You know, are you laughing at me? Okay. All three of these problems are easy to solve, but I hope you can see that managing dependencies is the key.
What is the solution?
You're not worthy. You know? No, the truth is, there's only so much you can cover in an hour. You know, I'm trying to, you know, if I told you, then I wouldn't have a job, and then, you know. No, I'll tell you the same thing I tell my students is, you know what? My gift to you is allowing you to ponder the question, and you know, is pondering the question. You can help. Maybe we can talk, but answering it too soon would be immoral. Okay. Yeah, and so one of the games here, and I mean that quite seriously, one of the games here is to recognize that things fail in parallel differently than they fail in ordinary programs, and they fail in catastrophically different ways. And let me give you some advice, and you will ignore it, but I hope that when you ignore it, you hear me nagging you. You know, one of the things that's going to happen in the next few weeks is your program is going to not work. I know that's hard to believe, but you know, the next few weeks you're going to work on some code, and you know, I'm going to go out on a limb here and say that your code is not going to work sometimes, and your first temptation is going to be to blame the computer. You know, it's the MPI library, or Stampede's having a hardware problem, and I'm here to tell you, it ain't. Okay? I'm here to tell you that Stampede does have bugs. We do have hardware problems, but you will serve yourself well if your mindset is that that is not your first assumption, because it's probably not going to be the case. Okay? Avoid the temptation to blame the environment. Learn to use parallel debugging tools. There really are such things. And test serial versus parallel often. I'm going to go back to serial, test it on 2 cores, test it on 2 nodes, and you know, don't fire it up too big too quickly. You know, gee, it works. Let me see how it works at 1,000 cores. No, that's not the best approach. Okay. Another question I get a lot, and I think in this audience this is a really important question. You know, you're all working for, you know, not quite 12 professors, but maybe 8 or 9 professors, each of whom has his or her own needs, own disciplines, own tools. And so the question is, you know, does this stuff apply in the tool set that my boss is going to want me to work? Because after all, you know what the most important and best tool set is? It's the one your boss has, okay? It is absolutely true that most parallel work is done in Fortran, C, and C++, and there's some good reasons for that. But the question is, can I use other tools? And the answer is yes, okay? There are more and more maturing capabilities in other languages. You're seeing, for example, if your research project is in R, or if it's in Python, or it's in MATLAB, or it's in Octave, you're seeing more and more what are called wrappers. You know, basically, you know, code that allows you to call MPI from these languages. You're seeing more and more examples of these languages calling MKL. Our little secret, right? Okay, calling MKL under the hood in ways that exploit the money, and that's worth knowing. There are some people out there who are traditional parallel high-performance computing bigots, you know, who kind of want to say, you know, if you're not C in Fortran, you're just not bad enough to be in this business. Well, that's a lot of baloney. Okay? There's room in this business for an expanding set of tools and needs and disciplines, and I'm here to tell you those capabilities are maturing. If you're really looking to make Stampede fly, you're going to do it in Fortran and C. But if you're also measuring your productivity in terms of human labor, you're going to get some nice parallelism out of some of these growing sets of tools. There really are utilities that understand parallelism. There are parallel debuggers. There are profilers that will allow you to see how your code is doing, whether or not one core is waiting for another core, those sorts of things. And the more sophisticated your needs, and really even early, the more you want to do that. There's so much more to say. You know, I could keep you for years and I'd enjoy doing it. But let me give you the big ideas. I mean, I'm not kidding when I say to you that you cannot become a parallel programmer in a day. And I'm not kidding when I say to you I'm not trying to achieve that. I hope you've sensed that. You know, we've had some fun, we've teased, but I hope what I've done is give you some memorable metaphors. How many? About? You're in computational science and you're giving me this about stuff?
I didn't want to count the waste of time.
Did he just say I didn't want to? Okay. There are 17 metaphors. Anyway, I really want to give you some big ideas that you can hold up to the light and sort of keep in mind as you get immersed in details. And let me tell you what I consider the biggest ideas. First, the distinction between shared and distributed memory. It's amazing how many people, smart people, accomplished people, lose track of the distinction and start to say, why isn't my program working on 200 cores? Well, because your program is an OpenMP program that can't work off of a node. You know? And so this idea of shared versus distributed memory, this idea that OpenMP and MPI are not really competitors to each other. They're not alternatives for doing the same thing. They do two very different things, and they each have their place. Understanding that distinction is important. And it's not a matter of one right and one wrong. It's not a matter of one's better, one's worse. They are programming models that are targeting architectures, and those distinctions are important. Second, realistic expectation. Your application has a sweet spot. It may be 100 cores, it may be 10 cores, it may be 10,000 cores. It may depend on the quality of the programming in ways that you can affect. You may be able to improve the program so that it can scale from 100 cores to 1,000 cores. Or you may be able to improve the program so it can work on this larger data set. But there are limits to scalability. Amdahl's law says there's only so much you can achieve, and Amdahl's law is based on perfection, and you don't have perfection. There really are costs of coordination. And so understanding the sweet spot is going to go a long way. In fact, I'd go further than this and say, you know what? Scale up gradually. When you first go to Stampede, run your program on 1 core. And then try it on 2 cores. And then try it on 16 cores, because that's 1 node. And then when you got that working, try it on 2 nodes. See if you can work across nodes if you're capable, you know, if your program's capable of doing that. Don't go on to Stampede and launch a program on 24 cores, because I can tell you it's not going to work. Work out the kinks gradually, scale up gradually. While there's many other things that I would say are important, I would also say this. The bad news is this isn't free. It takes some work, and some of that work is really, really hard work. But this is so cool. It's worth the effort. It's worth the effort in terms of the value to society And in terms of the genuine intellectual joy comes from the accomplishment. And so I conclude by saying, welcome to this world. You're going to love I just did. I hope.
I mean, like in general.
In general, I haven't yet tried.
Oh.
Not a lot. I will say that. Are we disconnected now?
I'm saying Johnny's gonna come in, but I think I'll just stop the hangout.
Why don't we agree that we're going to crank back up at 20 till? Okay, we'll take a 15-minute break.